Welcome everybody. I would like to show the progress of the LaTrappe case 6 of the NextGen project. So relevant data, I think it's a rather large system with about 360 cubic meters per day. It's an equivalent to 10,000 people's equivalent, although it is brewery water. And it's a water circularity showcase, and it's being performed with partners Biopolis, IP Star and Waterboard de Dommel. Now it's quite a famous brewery. That's the setting, and the goal is to, based on the principle water-based urban circularity, where food, energy, and waste systems are built around a regenerative and sustainable water cycle. The last thing, it builds upon the already built metabolic network reactor technology by Biopolis, in which plants are used as an addition to bacterial compartment. The main objectives, so combine the metabolic network reactor with nutrient and water recovery for fit for use industrial reuse, maybe even up to water for beer production, but that is severely dependent on the quality of the water that we achieve. Now, also, it is a biomakery concept for water reuse in decentralized areas, and ultimately also carbon, nitrogen, and phosphorus recovery with nutrients removed from the water, and they can be converted into fertilizer for plant or microbial protein. If we position it within the circular economy, what we see is a technology evidence base, and LaTrappe is both located near the wastewater nexus on the water end side, but also with a close connection to nutrients and material recovery. This is the current situation. So we have the Abbey, then there is brewery wastewater, restaurant wastewater. They're being treated in the metabolic network reactor, and ultimately, in order to prevent drought in the local area, the water is discharged back into the canal, so maintaining the local water cycle. Now, to that, we're going to add some Melissa inspiration. So, for example, on the Concordia research station in Antarctica, there was, for 8 years already, a semi-autonomous system in operation that is recycling the gray water, and the aim is not to contaminate the pristine environment on Antarctica. It's showed to have very limited maintenance requirements, and it's based on also the plans from the Space Agency for manned missions into space. Now, another system inspired on this was the system I have been working on at Ghent University. It's a combination of urine treatment and gray water treatment, and the whole recycling aimed at high water recoveries. Ultimately, we reached 86% there. So this is how the system looks like. So it's quite an advanced treatment system with 5 compartments, 5 stages that are all neatly working together and controlled to PLC. If we look then, based on these inspirational systems, we aim to actually expand what is being currently done at the brewery. So we have the metabolic network reactor from which either sludge or water is coming that could be fed to a Melissa C2 inspired photobioreactor for microbial protein production. But it could also be the wastewater coming out of the metabolic network reactor could also be fed to a similar system like the gray water system, in order to get a higher water quality and be able to reuse it at the brewery or in the restaurant. Current situation, so we've been operating the metabolic network reactor, or it was been operation by Biopolis. There were some issues with regard to the stability of the influent, and also the situation related to Corona. So therefore what we have observed is that the system has the ability to reach the required water quality, but due to other fluctuations is not always able to meet it. So sensitive to fluctuations in the brewery mostly. Now, to add this Melissa system to improve the performance of the water quality, or the water quality reached. So for this purpose, we sent 5 liters of raw brewery water to France, to Melissa partner Firmus, and was operated with ultrafiltration and the reverse osmosis, and ultimately the water was clean. And it has to be said this was raw brewery water, so it was a quality worse than what we actually get from the metabolic network reactor. Now from there we went up to from about 2400 microsiemens per centimeter, and you see the color, the middle one being the concentrate and the right one the permeate that is being produced, and ultimately down to 180 microsiemens per centimeter. And I will spare the details on the exact performance parameters. The system is a so-called purple bacteria reactor. What we've known is that from the more axenic type of reactors that are used for the space agency, we've opted for a relatively more open type of system, this one actually is relatively more cost effective for these type of environments. Now what we have done also is modeling in order to make sure that we can manage the growth in a more mixed culture operation that we were aimed for here, and this is in collaboration with Melissa partner University of Antwerp. Here you see some more results from the photobioreactor. What we see is that the wastewater is really turning purple, meaning that there is indeed, as we predicted by the model, a significant population of purple bacteria growing into the system that can later be harvested. Now, what are the lessons that we've learned? So first of all, we need a relatively close interaction with the brewery, because especially in these times where production is stopping and restarting, cleaning is happening, it is very important to communicate, especially with the biological system as the treatment that is sensitive to the upsets, for example, high pH. What's furthermore important is a relatively decentralized system, so it's not like most of the wastewater treatment plants operated by a large party or a water board, for example, and therefore it is reliant on very few operators, and also both operators actually got corona, and also therefore that for some time really reduced the severity in which the system could be operated, causing some major issues. Now, I think from that perspective, it's very useful to have a remotely controlled physicochemical treatment to provide redundancy, as we are currently planning with the Melissa greywater inspired system. Now, furthermore, it's an interesting solution if we look at the purple bacteria, because they do grow well on the brewery effluent, even if it's raw, but it still requires a relatively large surface area, so that's something what we're looking at. Fluctuations in the quality seem to be relatively stable in terms of allowing the growth of the purple bacteria, but of course it could be, and that's something that needs to be tested in the future, is that the quality of the biomass would be affected, and therefore it could not be used for all the type of applications that we're intending to. Now, the last part, the operation in this case, is done by PhD and master students, postdoc and master students, and that's relatively highly skilled personnel. So that's something the system needs to be simplified and more matured in order to be able to operate it really as a full solution. Now, to the last step. Due to the issues with Corona, we have opted for a local collaboration rather than going for the system in France. And we have started collaboration with Jotum Waterbehandeling, and we can use their so-called smart box, with the nanofiltration as similar to the earlier WTUB inspired system that I showed. And we will test it both on brewery effluent, municipal effluent, and we will check to what extent the water reuse quality through QMRA and QCRA is reached, and also concentrate quality for the purple bacteria. If that is sufficient, will be tested. Now the system will be should be installed one of these days, so then we can really start seeing to what extent we can produce the fit for purpose water. Last one, we have also been working on a slightly improved version of the photobioreactor because we had some issues also with parts that could not be delivered, due to which we had some delays. Now we've produced, let's say, own-produced photobioreactor inside the container, and it will actually allow us to have much more control over everything that happens with the system, and also we expect therefore that the system performance will get better. Now that is also of course very scalable, because of course you can just stack multiple containers if needed, if a larger system is needed ultimately. So with that, I would like to finish my presentation and thank you for your attention. If there are any questions, feel free to reach out on my email.